Okay, welcome back. We were talking about these fascinating and mysterious things called neutron stars. We have seen that they can be made in the center of a normal type 2 core collapse supernova when the ball of what was supported by electron degeneracy pressure collapses and is now supported by neutron degeneracy pressure. These things are extraordinarily dense, as we've seen. But what are they like? How big are they? What does that look like? How do we see them? So let's talk about neutron stars some more. We've talked about the size of a neutron star as being about 10 kilometers. But let's think about what that is just in terms of nearby, because 10 kilometers is a number. Most of the numbers we talk about in astronomy, you can't really wrap your head around. This is a number you can wrap your head around. This is centered on the ISC in Geneseo, what a circle of a diameter 10 kilometers looks like. It's not that much bigger than Geneseo. Here is 390 you can see coming down from the top. Here is the Wegmans Plaza out here. Here's Beaufort. It does not reach to Conesus Lake. It does not reach to Mount Morris or even Leicester. And so that's the size of a neutron star. If you take a neutron star and pluck it down and put it in Geneseo, well, bad things obviously happen, but that's as big as it gets. If you know Rochester at all, the closest big city to us, here is another diameter 10 kilometer circle drawn, centered on Dinosaur Barbecue in the center of downtown Rochester. And you can see this neutron star basically takes up the entire city of Rochester. It is about the same size as Rochester itself. That's what we're talking about when we're talking about neutron stars. Something that is reasonably large. You can wrap your brain around it, the size of this thing. What you can't wrap your brain around is how much mass there is squeezed down into that area. As we've seen, extraordinarily dense. 10 to the 17 kilograms per cubic meter. Cubic centimeter would weigh something like 100 billion kilograms. Unbelievably dense. Okay, so what do these things do? How do these things discovered? They were discovered in 1967, and it's an interesting story. There was a PhD student named Jocelyn Bell, who was a radio astronomer who was looking for things in the sky and was making some observations with her telescope. And she decided to do an experiment that had never really been done before, which was look for very fast time series astronomy using radio telescopes. Normally, when you're looking at radio telescopes, you're integrating over some long period of time, and any variation that is happening over on the order of even seconds to minutes is smoothed over, and you only are getting, the average of, let's say, over a minute or over 10 minutes or something like that. Jocelyn decided to look for very fast changing things. And what she found was there are certain things in the sky, a certain class of objects, that are not only changing on the order of seconds, but getting extraordinarily brighter and fainter over the time scale of seconds. This is an example of such a spectrum, a time spectrum. You've got time on the x-axis and brightness, let's say, in the radio on the y-axis. And you can see over the course of a couple of seconds, this thing goes from very bright to very faint, to very bright, and back to very bright again. And it repeats this ad nauseum as long as you want to watch it go. These things are coming from a spinning neutron star. We call these things a pulsar. Pulsars are not physically pulsating stars. This is one of the misnomers. We'll talk about pulsars more in the next few slides. This is why they call pulsars. You see pulses of light coming from them periodically. In this case, every second or two. Now, one of the reasons I bring this story up is because it's one of the great tragedies and injustices in Nobel Prize history. Not long after that, in the next couple of years, Jocelyn Bell's research advisor, thesis advisor, won the Nobel Prize for this discovery. In his acceptance speech, he did not even mention that Jocelyn Bell had actually done all of the work to actually discover this thing. And it wasn't discovered until some years later that, in fact, all of the work for this particular discovery had been done by somebody else. And so Jocelyn Bell does not have a Nobel Prize, but she should have a Nobel Prize for the discovery of neutron stars. She's still kind of a hero in the astronomy community, even though she didn't get her Nobel Prize. So what do these things look like in real time? Well, here is the Crab Nebula. If we had been on campus, we would have done a lab where we looked at the Crab Nebula and calculated how far away it was and how fast it's expanding and all sorts of interesting properties of the Crab Nebula. But one of the interesting, this is a supernova remnant, by the way. It's a supernova that went off in 1054, I think, AD. There are Chinese records of having seen it in the sky. It was a spectacular sight at the time. But at the center, so this is what it looks like 1,000 years later. And at the center, if you zoom way in on this spot right here, is one of these pulsars. And this is an extraordinarily fast spinning pulsar. Look at this time scale down here. You can see it blinking on. There's a secondary blink, there's a primary blink, there's a secondary blink, there's a primary blink, there's a secondary blink. And the distance between these primary blinks is 0.033 seconds. Whatever is happening, if this primary blink is the thing, it's happening 30 times a second. This primary blink happens 30 times per second. Things in astronomy just don't vary on that short a time scale. And there's a reason for that, and we'll talk about that in a second. But this Crab Nebula pulses, meaning it doesn't really pulse, but we get pulses of light from it 30 times per second. So what the heck is happening here? Here's another view of the Crab Nebula pulsar in X-rays on the left, in visible light on the right. It looks kind of looks kind of the same, but you can see some interesting features here, right? Even in the X-ray invisible. There seems to be a disk of material that has some preferred axis. You can sort of see it there. There also seems to be a jet of material moving perpendicular to that disk. This looks very similar, if you remember back to our star forming class, where we looked at propylids, baby stars that still have circumstellar accretion disks. It's the same sort of phenomenon here. You have a disk of material that's maybe accreting onto the surface of the neutrons, but you have a neutron star here instead of a baby star. And so the speeds at which things can get going are much faster. The temperatures at which things get heated up to are much hotter. Baby stars don't glow in the X-rays. Neutron stars glow in the X-rays. That's what we're looking at here. So we need to understand what pulsars are and how they can be changing in brightness that fast. We need to understand something about the making of a neutron star. So let's back up here and think about properties of stars that go way up when you're making a neutron star. Now, lots of properties go way up when you make a neutron star. If we were doing this in class, I would put it out to the audience and you could suggest things. Certainly things like the temperature, certainly things like the density, certainly things like that go way up in making a neutron star. There's two specific things that I want to focus on, which also go up. One of which is kind of obvious maybe, and the other one of which is not all that obvious. So let's do the obvious one first. I'll get my whiteboard back out. Uh-oh, that didn't work. There we go. Now we're back. Sorry for that. Funny story, I have Snap camera. I was Skyping with my niece and nephew who are, I don't know, 5 and 7 or something like that. And they were playing with Snap camera and giving themselves unicorn horns and all that stuff. So they made me get it also. That's the reason for that particular thing. Funny story. Okay, so anyway, what is happening with this neutron star? Two things go up that I'm interested in when you make a neutron star. The first is, so this is things that go up in making a neutron star. Great, two things. The first is, think about what happens when things go from very large to very small. The analogy that I like to make for this particular thing, which is angular momentum, being conserved is that a figure skater, right? You know, when a figure skater holds her arms out and she's spinning, and then she pulls her arms in, she spins a lot faster. Things that get small by conservation of angular momentum have to therefore spin faster. So the spin rate of this neutron star was probably spinning pretty fast when it was at the center of this star and was a ball of iron. But when it collapses down to a ball of neutrons, it is getting smaller by a factor of 100 maybe, and spinning therefore faster also by factors of like 100 or something like that. So that's the one that you might have been able to get. You probably would have gotten. The next one almost nobody ever gets because it's not all that something you think, not something you think about all that often. That is the magnetic field strength. So these two things go way up when you're making a neutron star. What happens basically is that, again, when we talked about magnetic fields in the surface, in the sense of the sun was like a dipole magnet. And you could trace the magnetic fields that went through the surface of the sun. When you collapse this thing all down, it drags those field lines with them and increases the strength of the magnetic field lines. The distance between these field lines represents the strength. And as you compact everything, it makes that a lot smaller and a lot stronger. You might be thinking, hey, if you know something about magnetic fields, hey, this is a ball of neutrons. There's no charge there. How is this magnetic field getting dragged along? Well, not all of the protons go away. Not all the electrons go away. Just most of them. This is a thing that's mostly neutrons. But it still does have some charged particles around, and enough of them that these magnetic fields stick around and are important and are very, very strong in these neutron stars. Great. So let's go back to our PowerPoint slide. Great. So we have two stars that go now. So let's go back, the bipolar jets. So I'm going to read these, and I'm going to go back to my whiteboard and sort of draw what this is going to look like. So you got bipolar jets. How does that happen? Well, bipolar just means out of the north and south magnetic poles. Jets means this stuff is getting ejected at high speed. The materials is ejected along these poles at high speed. The magnetic field causes the electron to spin rapidly. Photons emitted in a jet. Okay, so this is a lot. I'm going to sort of say these things and draw them, and hopefully that will be helpful in seeing what's actually going on here. All right, so let's go back to the whiteboard. And now let's imagine that we've got some disk of material out here. It's very hot. And this disk of material, again, is probably, this disk of material is hot, it's charged. This is an extraordinarily hot, a very hot object here. You know, we said white dwarfs are 100,000 Kelvin. This might be close to 1,000,000 Kelvin, even at the surface. This inner part of this disk is extremely hot. It's all ionized. There's all charged particles there. That can't physically cross these magnetic field lines. So if this is going to fall, this material is going to rain onto the surface of this neutron star, it has to do it along the magnetic field line themselves. So some of it gets put in this direction, and some of it gets put in this direction. But just like the Earth's magnetic field makes the charged particles from the sun impact the Earth at the poles, which is why we get the northern and southern lights, this material that is falling out of the neutron star has to be funneled along these magnetic field lines. And interesting things happen when this material sort of gets caught up in this thing that's rotating really fast. It almost always happens, and the process is kind of mysterious still, that material gets ejected, some of it at least, in a very fast jet moving up and down from the neutron star itself. And these magnetic fields, let's say these are electrons, these magnetic fields are still pretty strong here. And as you may know, charges in magnetic fields, they tend to spiral. So you get these electrons that spiral in these weird ways. And that spiraling electrons actually emit photons along the jet line as well in, say, the radio wave. And so when we're seeing these things in the radio, we're really seeing this radiation that's coming from these spiraling electrons moving off in the direction of the jets. Okay, so that's the picture of what's going on here, and it's rather complicated. But now let's add one further complication to it. Let's say that the rotation axis is not aligned with the magnetic field axis. What do I mean by that? Well, I mean, I've drawn the magnetic field axis. There's the North Pole, there's the South Pole. What if the rotation axis is like in this direction, right? So this whole thing is spinning in this direction, even as the magnetic field is pointing in that direction. Well, what's going to happen then? This jet of material is not going to be pointed in the same direction all the time. What's it going to do? It's going to precess. It's going to go around like this, right? And it turns out that for the Earth's magnetic and rotation axis are not perfectly aligned. We don't expect that many of these will be either. And so what this has is a beam of both materials and light that's getting swung around in all kinds of crazy directions. That's what we think a pulsar is. Here is a much better example of one than I have managed to draw. Let's go back to our PowerPoint slide. Here we go. And this is a much better diagram than I would be able to show you, showing just exactly what's going on here. So you've got the jet of material, which is this green. You've got the neutron star itself, which is red. You can see they got the magnetic field lines here. And let's say my mouse is over here on one corner. We're going to get a pulse of light now. Every time this thing goes around, we're going to get a little pulse of light. It's called the lighthouse effect, because this is a lot like a spinning lighthouse. If you're out at sea, well, let me go through these last few slides, and we'll talk about this. So this is the much better diagram than I was able to draw of what's actually going on here. You've got beam radiation going in both these directions. You've got a misaligned magnetic rotation axis, which swings around this beamed radiation. And every time this beam swings around, you get a little pulse of light from these axes, from this particular object. I call this lighthouse effect. It's very similar to that. If you were out in the ocean, this is exactly what a lighthouse looks like, right? It's very, very faint until that beam sweeps around, and then all of a sudden you get a flash of light. And then when the next one swings around, you get another flash of light. So this pulsars are beamed like that. It's sort of the lighthouse effect. Sure, get the same thing. So just to reiterate, pulsars do not physically pulsate. They are neutron stars that are just rotating really fast, and we're seeing pulses of light from them, which is why they're called pulsars. Okay, I'll go ahead and finish this. We've got, well, we'll need to set up the next class, which is well, let's talk about neutron stars. So why do these things have to be neutron stars? The circumference of a neutron star, again, 2 pi times the radius. If the radius is 5 kilometers, this gets us to about 60 kilometers in the circumference of a neutron star, the outer portions of it. The fastest pulsars that we can see are spinning 1,000 times per second. But even that one that's spinning 30 times per second is extraordinarily fast, right? And so if you do some math, take a particle on the equator of this neutron star that's spinning 1,000 times per second and is 60 kilometers in radius, you can do a pretty simple calculation to figure out how fast a particle on the surface of this object has to be moving. And it's 60,000 kilometers per second. That's 20% the speed of light. And it's about the escape velocity from a neutron star. So even though if you were to land on a neutron star, the gravity would be so intense that you would be a puddle of neutrons instantaneously, this thing can't physically spin any faster than that, or it's going to spin itself apart. And it certainly can't be any larger than this, because anything that's larger than this is going to have a larger circumference, and it's going to be moving even faster. And if you get much larger, if you get any larger, you're going to spin yourself apart. If you get much larger than that, you're actually going to be going faster than the speed of light, which we know actually can't happen. So anything beside the neutron star could not be spinning this fast, could not be spinning this many times per second, or it would just be torn to pieces. So we know these things, at least the fast ones, and almost all of them have to be neutron stars. Nothing else could spin that fast. Even a white dwarf would be torn to pieces instantaneously. Okay, that's neutron stars. They're cool. There are lots of good stuff. What about very massive stars? It turns out if your supernova remnant, meaning that the ball of neutrons that you have left over, is greater than 3 solar masses. Remember, there was a limit to how massive a thing you could make with neutron degeneracy pressure, with electron degeneracy pressure, which is 1.4 solar masses. Turns out neutron degeneracy pressure is stronger than electrons, but it's still, there's a limit after which you can't support the thing by neutron degeneracy pressure anymore. So if you have a remnant that is greater than 3 solar masses, it can't collapse into a neutron star because now neutron degeneracy pressure doesn't work. What happens? We at this point know of no force that can support the star beyond further collapse. And so we think this thing that is greater than 3 solar masses and made of neutrons will just collapse into nothing. The neutrons will go away and it will into nothing, meaning something that's even denser and more exciting and cool than a neutron star. But that is where we will end class for today. And on Thursday, or later today, if you just want to keep watching these in turn, we will figure out what those things actually collapse into. And I'll give you a hint by showing you the next chapter, which is black holes and curved space-time. Come back. Next class is Black Hole Day. Hope to see you there.